Hello and welcome to Module 14 in our C language series. Today's session is going to focus on dynamic allocation. Just a brief introduction before we begin our discussion on dynamic allocation. C, the language supports two kinds of memory allocation through variables. One is static and the other is automatic allocation. But there's a third type of memory allocation that is not supported through or by variables, and that is what is referred to as dynamic allocation. Now, before we get into our discussion on dynamic allocation, let's first understand static and automatic allocation. So what is static allocation? Static allocation happens when a static or a global variable is declared. Important to note that static allocation happens only once at the start of the program. And so each variable, that is each static or global variable, occupies a block of memory space of fixed size. Second important point to note is that this size needs to be determined before the program begins execution. Also, it cannot be changed during program execution. Space is allocated when the program starts executing. And as I mentioned earlier, cannot be changed during program execution. Also important to note that memory allocated using static allocation is never freed. So this memory will be freed only when the program ends. Coming now to automatic allocation. What is automatic allocation? This happens when a local variable or a function argument is declared. And so memory is allocated when the compound statement containing the declaration of this local variable or the function argument is entered. So the compound statement here, as you may have already figured out, is referring to a function. And we talked about this in our earlier discussion, right, on functions, when we spoke about how local variables will be assigned their values when the function is entered and will lose their values when the function exits, right? And so using automatic allocation, the memory will be freed when the compound statement is exited. Compound statement again meaning the function. Coming now to dynamic allocation. What exactly is dynamic allocation? So think of it as being able to allocate memory while the program is executing, right? So on the fly, if you will. And so it's defined as a technique wherein a program, while executing or running, determines where to store information. When do we need to use dynamic allocation? When we do not know memory requirements of our program prior to program execution, for example. And so we will need to use dynamic allocation when the amount of memory required and for how long it is needed is dependent on factors that are not known before program execution. So take, for example, you're reading strings from a file and you don't know the length of the string. So there's a really long string. So what do you do then? So you keep allocating memory dynamically as more and more of that string is read. And this is a case for use of dynamic allocation. Take another case. Let's say, for example, you have a structure. You can see that structure has got 60 bytes, right? And we can allocate 60 bytes and read one record. But we don't know how many records are present in the file. So what we do then is using dynamic allocation, and within a loop, of course, we keep allocating 60 bytes in that loop dynamically. And then we are able to read every record from beginning to the end of file. Now a question may arise, is there a storage type that we can use called dynamic? And the simple answer is no, there is no storage type called dynamic. In fact, the only way we can use dynamic allocation is through calls to library functions. And the only method we can use to access the values that are stored in memory spaces that are dynamically allocated is through the use of pointers. So we can never have a case of a variable in C whose value we can take and store in a dynamically allocated space. Now, having seen that we can allocate memory during program execution, It's tempting to use dynamic allocation over static and automatic allocation, right? Because we can have full control of memory. We can allocate how much we need and when we need it. We can also, by the way, use a library function to free that memory. And so it's really tempting to use dynamic allocation. The question then would be, should we always opt for dynamic allocation over static and automatic allocation? And the answer to that is no. Why? Because first of all, dynamic allocation is less convenient to use. Why is it less convenient to use? Because for one, we could run into issues like memory leaks, where we are allocating memory and then we are not freeing that memory. Or we could run into a situation where we have run out of memory. And another important point is using the dynamic allocation system requires more computation time. And so we will use dynamic allocation only when program requirements cannot be met with static and automatic allocation. Now, where is this memory allocated from? To understand that, we will take a look at a visual that will give us a conceptual view of the layout of memory in terms of a C program. So here we have the program occupying what is called the code segment of memory or the text segment. Then we have global and static variables occupying what is known as the data segment in memory. Then we have the heap, as you can see, that has an arrow going upwards. And we have the stack, which has an arrow going downwards. Right? Now, what is the meaning of the up and the down arrow? So this comes from early computing times when there was really limited memory. And so the heap would start from a lower address going upwards, and the stack would start from a higher address going downwards, so as to give both of these equal access to that limited memory. Now let's talk about the stack. The stack is where local variables and function arguments are stored. How do we determine the amount of memory required for the stack? Well, that depends on the design of your program. For example, whether you have recursion or not. And speaking of recursion, would a program with many recursive functions take up more memory? And yes, it would. Because remember, local variables are stored on the stack, and recursion involves a function calling itself. Every time the function is called, the local variables would be stored on the stack, right? And so, of course, that would require more memory on the stack. Now, what about the heap? The heap is where memory for dynamic allocation comes from. What about the size of the heap? How is that determined? Well, the size of the heap is limited only by the amount of physical memory available on your specific machine. So if the function that we use to dynamically allocate memory returns a null, then we know that there's no more memory left on the heap. Coming now to the functions of the dynamic allocation system, we have malloc, we have free, we have calloc, and we have realloc. We'll talk about one more function a little later, but these are the basic four that you need to know. Talking about malloc, malloc is used to allocate memory, so a portion of remaining free memory is allocated when malloc is called. What about free? When free is called, memory is returned to the system. What about calloc? It allocates memory just like malloc, but it also initializes that memory region to all zeros. And so calloc would call the function memset. Remember, we discussed memset earlier. So it could call memset to initialize that region to zeros. Why did I say could? Because it could also be a situation where it may not call memset. When would that situation arise? When calloc determines that that region already has zeros in it, right? We have realloc. What's realloc? Well, that allows us to increase the size of the previously allocated block of memory. Now let's take each of these in detail. So we have malloc, allocating a block of memory. The prototype here returning a void pointer. A void pointer, why? So that then it can be assigned to any data type. That's the reason. And you can see the argument is a size t type size. And so this function returns a pointer to a newly allocated block of length size bytes. or a null pointer if memory could not be allocated. So on failure, malloc returns a null, right? The contents of the block are undefined. What does this mean? The block of memory that is allocated by malloc will contain junk, and therefore it is incumbent on us as programmers to ensure that the block is appropriately initialized. So normally you would initialize a return value to a pointer pointing to the type of data that you want to store in this particular region or block of memory. Always verify that the return value is not a null pointer, right? So we need to check every time the return value of malloc for a null pointer. Why? Because if we try to use a null pointer, this will usually result in a system crash, right? Important points about malloc. Every call to malloc needs to be checked for a return value. That is, if it is null, the block allocated by malloc can hold any type of data. Why? Because remember, it's returning a void pointer that can be assigned to any data type. On GNU systems, the address is always a multiple of 8 for 32-bit systems and a multiple of 16 for 64-bit systems. Memory located after the end of the allocated block could be in use for something else. And so what happens if you treat the block as longer than you asked it to be? If you try to access the memory beyond what you asked to be allocated, then you could be destroying data that belongs to another block, for example, or you could be destroying data that malloc itself uses to track the allocated memory blocks. And so we got to be wary of that. Coming to calloc now, allocates memory and clears the region to all zeros. Like I said earlier, it may or may not call memset. The prototype, as you can see, returns a void pointer taking as arguments size t count and size tl size. And so it allocates a block long enough to contain a vector of count elements. So when we're talking about a vector of count elements, think of an array, right? And each of the elements will be of size L size. The contents of the block will be cleared to 0 before calloc returns, right? Again, as I mentioned, may or may not call memset to do that. Now write some code. Write code to allocate memory to an integer array of size 100 and initialize the block allocated to all zeros. So to do that, let's go to code blocks and we can start a new file. Hashtag include stdio.h, hashtag include stdlib.h, and hashtag include malloc.h. That's where calloc is defined. Int main. And here we will have int star I, the pointer to an integer, and then counter. And now we'll use I to get the return value of calloc. I is equal to calloc 100, right? That's the number of elements, comma, size t type of argument, which will be size of int, right? And now we will check if not I, which means if I is equal to null, then printf error allocating memory aborting, and then exit 1. Otherwise, we want to see that calloc has actually put in zeros, for example. So what we can do is we'll say for counter equal to 0, counter less than 10. We're not going to check all 100 places, just the first 10, counter plus plus. And this is just for our reference so that you understand how calloc works. Printf %d \n, comma, I of counter. right? And then of course here exit 0. If we run this now, and you can see we have those 10 zeros, right? I hope that's clear. Moving on. Realloc. So when would realloc be used? When programmers do not know for certain ultimately how big of a memory block they need, right? And so realloc can be used to make the memory block longer. This is we saw in the previous slide in the example of that very long string, right? So the prototype of realloc is like this. As you can see, the function returns a void pointer so that it can be assigned to any data type. And then we have two arguments, void star ptr and size t new size. Now ptr of course would refer to the previously allocated block, right? The one that we're trying to make longer. And so realloc changes the size of the block whose address is ptr to new size. So what if the space after the end of the block is in use? So what realloc does in this case is it will look for another region, right, that will satisfy the size required, and then it will copy the contents of this current block to the new region and return to us the new address, right? What happens if no memory is available? Well, then realloc will return a null, which means realloc fails, and if realloc fails, the application can anyway not continue because it is out of memory, right? Now write some code, allocate space for the following string, copy the above string into the space allocated, increase the size of the memory block previously allocated so as to place a period at the end of the string. Now again, we go to code blocks and let's start a new file. And hashtag include stdio.h and hashtag include stdlib.h. Int main, and here we'll have char star str1 and star ptr, and we check here if not str1 equal to malloc. Malloc is defined, by the way, in stdlib.h, and we are going to ask for 34 bytes to be allocated. Why not 33? Because remember, we need to make space for the null character as well to terminate the string, therefore 34. Right? So if malloc returns a null, then printf allocating memory, aborting, and exit 1. Right? Otherwise, ptr, and we're going to use memmove destination str1. Now you can see that I'm not getting the prompt. What am I talking about? I'm not getting the prompt in terms of memmove and its arguments. So then it should immediately strike you that you need to include another header file. Which one is that? String.h. Right? So now you will see when I use memmove, I'll get all these arguments. And so we provide the destination, right, which will be str1 and that string, comma 34, right, to accommodate the null character again. And then we can printf the string to see that memmove worked, just for our reference. So printf %s \n, comma str1. Now we can use realloc. So str1 equal to realloc, and we pass in the arguments, which is str1 first, followed by size t new size. What should be the new size here? Remember, we need to put in the period plus this new string has also to have a null character. Instead of 35, we'll put in 36. Right, so we're asking for 36 bytes there. And we'll check here if not str1, means if a null is returned, then printf error increasing size, and you can say aborting again, and then exit 1. Otherwise, we'll use memmove now and provide source and destination. So what is the destination? str1 plus 33, right, comma, we want to put in that period, and comma, we need to specify size, that will be 2, one for the period and the other for the null terminator. And then of course we can printf the new string, so %s \n comma str1, right, and then exit the program, so exit 0. Let's run this now. And there we have the original string and the one with the period at the end. Okay, so I hope that's clear. Moving on. The free function. Used when a block of memory is no longer needed. Remember, we need to free memory. The prototype here returns nothing. As you can see there, just a void, and takes as argument void star ptr. ptr again referring to the block that we want to free or deallocate. Deallocates the block of memory pointed to by ptr, frees that memory. Right, now freeing a block alters the contents of the block. What does that mean? So say we have something like this, as you can see block 1, and you can see part of this particular block has got the address of the next block. Right, so it's pointing to the next block, which is block 2, and block 2 has got the address of block 3, and block 3 is pointing to block 4, block 4 is pointing to block 5, and block 5 is pointing to block 6. Block 6, as you can see, has got a null at the end, indicating the end of this chain. Now this is commonly what would be known as a linked list, and we'll talk about linked lists in detail in a later session. What we need to understand for now is that if we release the first block, then we're going to lose vital information. What is the vital information? We're going to lose the address of the second block, right? And once we've lost that, then we cannot get access to the remaining blocks. And therefore, it's important that before freeing a block of memory, we need to make sure that if we need those contents, we copy them to another place and then free that block, right? So we can't just do something like this. We've lost the main link, you can say, in the chain or the head of the chain, right? Another important point we need to note in terms of the free function is that failure to deallocate or free memory dynamically allocated will lead to memory leaks. Right? And I spoke about this before, where we're allocating memory, but we're not freeing it. Right? Now, allocate space for 100 strings of 128 characters each entered by the user, then free the memory. So we're not going to actually take in 100 strings here. We're just going to do the exercise of allocating the memory and then freeing the memory. So let's now go to code blocks. And we start a new file. Hashtag include stdio.h and hashtag include stdlib.h. And we don't need really any other header file. If we do, we'll come back to this later. Int main char star str1, and that's going to be 100, and int counter equal to 0. And then for Now, since initialization is already done, we don't need to do it again. Counter less than 100, counter plus plus. And within this, we will say if not str1 of ctr, right, equal to malloc, and that's 128, right, then printf memory allocation error, and exit 1. Otherwise, printf. Now what we're going to do is, since there's a printf statement here, this is of course just for our reference, we will test this out just on 10 of these strings rather than on 100. Right? If it works for 10, it works for 100. After this, that is out of this for loop, we will free the memory. So for counter equal to 0, counter less than 10 now, counter plus plus, and we will just say a free str1 of ctr. Now you may want to print some message just for your reference. In that case, you can have this in a code block, and you can say here printf, and then of course exit 0 to end the program. Now we run this, and you can see we have memory allocated successfully 10 times and memory freed successfully 10 times. Right, so now I hope you got the idea of how to use malloc and free. Moving on. Alloca. Now this function, as you can see from the prototype, returns a void pointer, again can be assigned to any data type, and takes as argument size t size. Allocate size bytes of memory from the stack now, not from the heap. That is not from free memory, but from the stack. Advantages, that is very fast and causes no memory fragmentation. But what is the meaning of memory fragmentation? So let's look at a visual here. We have the heap, that's free memory. And let's say we've allocated 10 bytes, then 20 bytes, then 30 bytes. Now we want to allocate 40 bytes and we have 10 bytes free. But of course we can't use our 10 bytes, right? So we'll have to look for another region in this heap for those 40 bytes, which means is 10 bytes remain unused. And so when you have little pockets like these that are unused, that is what is known as memory fragmentation. Now malloc may cause memory fragmentation, but having said that, the implementation of GNU in terms of malloc is such that it does not, or it minimizes memory fragmentation. So we really need not worry about that. Alloca returns a pointer to the beginning of the allocated space. A null pointer is returned if the allocation request cannot be honored. Memory allocated is automatically freed. So that's another advantage when the function that calls alloca returns. But there are some disadvantages. Alloca is less portable. So yes, it is supported by GNU systems, but it may not run on other systems. Also, trying to allocate more memory than the machine can provide does not give us a clean error, but rather a segmentation violation. And those, if you've talked to seasoned programmers or developers, are the most difficult to resolve. In any case, let's write some code, allocate 70 bytes from the stack. So to do that, let's go to code blocks and we start a new file. And hashtag include stdio.h, and then hashtag include stdlib.h, and then hashtag include malloc.h. That's where alloca is defined. Int main, and we have char star str1. Let me check if str1 equal to alloca, and that's 80 bytes, right? Then printf, right? Else printf and exit 1, right? And here we just say exit 0. We run this now. And there we have it. Right, so memory is successfully allocated from the stack. So I hope that's clear. This ends our session for today. In the next session, we will be talking about miscellaneous functions before moving on to algorithms and different kinds of sorts. The graphical module, I have moved to the last part of the series because we need to uninstall the current configuration of the IDE we have, that is code blocks, the 64-bit version. We need to work with the 32-bit version for graphics, and so that will be done at the end of the series. Right, so see you in the next session. Till then, take care, stay safe, bye.